concentrates on reduction and reducing agents. So in this lecture, we will cover the following: a definition of reduction and reducing agents. We'll look at specific reagents, including metal hydrides as reducing agents, organometallics as reducing agents, and hydrogen gas as reducing agent. And last is dissolving metals as reducing agents. So let us look at some specifics here. Reduction. As we have covered in a previous chapter, reduction is the supply of electrons. Notice electrons, and remember that electrons are negative. So reducing agents supply electrons, and that process is typically accompanied by a supply of hydrogen. Metal hydrides are one category of reducing agents. As the name suggests, hydride. We know from previous chapter, a hydride is a hydrogen with a pair of electrons, such as shown here. But of course, as you know, an anion cannot exist by itself, so it has a counter ion, a cation, to make it a neutral molecule. Here are some examples. Sodium hydride. Here's a hydride. So that's your reducing agent. Potassium hydride. Here's a hydride. H minus with an unshared pair of electrons. Another one that's commonly used that we covered in an earlier chapter is lithium aluminum hydride. Notice the name again, hydride. And here is the H for the reducing agent. Another one is sodium borohydride. Notice again the name, borohydride. So these are all good reducing agents. Let us see how they actually work. As I mentioned, lithium aluminum hydride, LiAlH4, is a very common reducing agent in organic chemistry. So it literally supplies an H minus, one of the H's as H minus, to a carbon or a center that's electrophilic. Remember here, electrophilic is partially positive, electron loving. So this reaction takes place because of the H minus, negative, reacting with the carbon positive. In the process, of course, as you know, you can't have more than 4 bonds to a carbon. So once this bond is formed, these electrons swing out onto our oxygen to make O negative. This, of course, as you see here, it is a salt. O minus Li plus is a salt. So in organic chemistry, we prefer to have the molecule instead of the ionic salt. So in the presence of an acid, we have an acid-base reaction. Here's the base, and here's the acid, and it's neutralized to give here. You will recognize this functional group here as an alcohol. So once again, you can reduce a ketone or an aldehyde using lithium aluminum hydride to supply H minus to form an alcohol in a 1 and 2 step reaction. Notice 2 steps. Some specific examples here. So if you had this ketone, and in step number 1, again, please include 2 steps if there are 2-step reactions, is lithium aluminum hydride. It's a reducing agent, so it will supply H minus, including this bond right here. And of course, in a second step here, we will get the H onto the O to be the alcohol. Notice that's a secondary alcohol from a ketone. secondary alcohol from a ketone. If you had a reaction with an aldehyde, you can imagine that would be a primary alcohol. Here's another example. Different functional group this time, a nitrile, but the same concept applies. Partial positive carbon, electrophilic, indicated by the partial positive charge. Lithium aluminum hydride is H negative. So therefore these electrons here will react with this carbon as shown here to form an imine, and of course that also has the possibility of being reduced with a second mole from the lithium aluminum hydride to form an imine. Some examples. So we have here propanol, an aldehyde, reacting in step number 1 with lithium aluminum hydride, followed by step number 2 with acid and water. Sometimes you'll see that as acidic workup. What you'll get here is an alcohol, and it's a primary alcohol. So primary alcohols come from aldehydes. Ketones react with lithium aluminum hydride, followed by hydrolysis to give an alcohol functional group here, and that is a secondary alcohol coming from your ketone. Let us turn our attention now to another type of reducing agent, and this one is called the organometallic. As you can imagine here, this one does not involve H minus but R minus. So the same type reactions will occur as we have seen with the hydride, but in this case it delivers not H minus but R minus. We have to make them. They're not easily purchased in the stockroom, so we have to make these. Let's see how we make them. You started with an alkyl halide. Here's the halogen, reacted with lithium. Notice again, lithium is to the extreme left of the periodic table, very electropositive. And what happens? It's a reaction to give RLi. Almost ionic, because Li here is electropositive, which makes R negative here electronegative, which means that the carbon is nucleophilic. It has a negative charge with an unshared pair of electrons. This is called an organolithium, as you can see here. Another type organometallic is the organocuprate. Gilman discovered this reaction, so it's known as the Gilman reagent. You take your RLi that you made here and react it with copper iodide. In the presence of a solvent, you get R2CuLi. Main thing here is that the R is partially negative and the CuLi is partially positive. One that's used a lot in organic chemistry, most commonly used organometallic, is the Grignard reagent, where there is magnesium that bonds to the carbon. So let's see how we make that. We start out here with Rx or R halide, could be chlorine, bromine, or iodide, reacted with magnesium. And notice again, magnesium is to the left of your periodic table, so therefore it is electropositive. The reaction is that this magnesium inserts itself into that bond to form that RMgX. The process is, or the outcome, however, is that this R is partially negative. It has a pair of electrons or closely associated with it, which makes it a good reducing agent. And of course it's partially ionic because this portion here is MgX or MgCl if the X were a Cl. This reagent, discovered by Victor Grignard French chemist, is known as the Grignard reagent. So we'll use that term or that name a lot to make reference to this specific organometallic reagent, which is the organomagnesium. Why? Because it's much cheaper to make using magnesium instead of potassium or lithium, as we saw earlier. So it's commonly used in organic chemistry. Let's apply this. So we have here the Grignard reagent that you can make from Rx. But here's the Grignard reagent reacting now with a ketone or aldehyde. Remember, this is the functionality carbonyl for a ketone or aldehyde. The difference is if this were an H and this were an R, that would be an aldehyde. If both groups were alkyl groups, that would be a ketone. But the bottom line is we have here R negative reacting with this electrophilic carbon here. Remember, opposites attract. You can't have 5 bonds to a carbon. So once these electrons come in to make a bond here, as shown here, these electrons have to go out on the oxygen to form a single bond, and of course a negative charge here. So this is your salt. The difference between this salt and the previous one using lithium aluminum hydride is that we have introduced here an R group, an alkyl group, instead of a specific atom, hydrogen. In a second step, this salt can react with an acid. As you can see here, it's basic because of that O negative. So if it reacts with an acid, we put on a proton here to form an alcohol. Again, an alcohol, but the difference here is that this alcohol has an R group instead of an H if you use a Grignard reagent or an organometallic reagent. Let us look at some examples. So reacting an aldehyde, formaldehyde, a specific aldehyde with a Grignard followed by hydrolysis, you get an alcohol. In this case, it's a primary alcohol because this is a specific aldehyde, one carbon here, and we're introducing another carbon. If you react an aldehyde with a Grignard followed by hydrolysis, what you get is a alcohol, but a specific type alcohol known as a secondary alcohol. Recognizing these as primary or secondary will be very important when we do the applications of these reactions. Let's look at a third possibility here. So this is a ketone in this case. A ketone reacting with a Grignard followed by hydrolysis gives an alcohol, but in this case it's a tertiary alcohol. Notice that this R, or this methyl group here, is coming from our Grignard. So you'll see in a second that we'll be asking you to synthesize molecules of this type, and you will have to recognize what will be your starting reagent and your Grignard for that reaction. And last example here is the reduction of carbon dioxide, a specific molecule again. As you can imagine, this is partial positive and this is partial negative. Likewise over here, partial negative. So this Grignard, which is negative, will react right here, and these electrons will swing out on the O to form O negative, followed by H plus. What you have here is a carboxylic acid. So once again, a Grignard reagent reacts with carbon dioxide to give a carboxylic acid, a very specific functional group. But in this case, we have here one carbon from the Grignard reagent and one carbon from our carbon dioxide. That will become very important when we start looking at synthesis if you're trying to make a carboxylic acid. Let us look at the application of this process here, or this concept. So let us say a question on the quiz or on the exam is show how to carry out the following transformation. Synthesis. So starting with this material. So that is your starting material. So you went to the stockroom and you found cyclohexanol. And your job was to make this as your target molecule. So when you're done, how do you make this target molecule here from this molecule, supplying appropriate reagents and reaction types? So as I pointed out, you will have to carry out the observations and a process called retrosynthesis, or working backwards. So let us carry out the observations here first. First observation is that this molecule here has two carbons, two additional carbons that's not in the reactant. Therefore, whatever you use here, it has to have two carbons added to this cyclohexanol to make this product. So again, make sure that the number of carbons on the reactant side is equal to the number of carbons in the target molecule. Another observation is that we'll have to make this bond because it's not here. So we'll have to make that bond. How do we make that bond? Another observation is that this alcohol here is a tertiary alcohol. And we just saw from the previous slide, we can make tertiary alcohols by the reduction of ketones using a Grignard reagent. So hopefully you can see that you'll spend a lot of time observing, making observations about your target molecule and working through a retrosynthetic strategy before you actually put pen to paper. Now that you've figured out what needs to get done, now you can put pen to paper and try to recognize the reaction types and the reagents that are needed. So, a quick summary here. You need two carbons as a reactant. You need to make this bond. This is a tertiary alcohol, and you can make tertiary alcohols by the reduction of carbonyls, specifically ketones, using a Grignard reagent. Let's put that together and see what we get. So working backwards from here, you can see here, if we had this ketone, we can use this Grignard here. Notice this is our 2-carbon Grignard to make that group and also to make that bond. We need an acid because we need to put on that proton. So this is the reduction of a ketone here using a Grignard reagent. Notice again, you don't have to use a Grignard reagent. You could use another organometallic, as we've discussed before, like an organolithium or an organocuprate. So this gives versatility to your possibilities or your solutions in solving these problems. Once you have recognized that you need a ketone, you know that an oxidation reaction here from an alcohol can give a ketone. So right away you know that you need a strong oxidizing agent such as potassium permanganate. Again, you need not use specifically potassium permanganate, but you can also use sodium dichromate in sulfuric acid, etc., those that we have discussed in previous chapters. Let us look here at further application of using the Grignard reagent. Notice when I say Grignard reagent, it's just a specific one, but it could be any organometallic. but the Grignard is specific to the magnesium. So let us say that you were asked to make this target molecule. Notice these are all the same target molecule. But the point here is that because this is a tertiary alcohol, you can use 3 different routes to make that tertiary alcohol using a ketone here and a Grignard. The first is, if you make this bond, putting on a methyl group here, using a methyl Grignard, you would need this as your ketone. If you had this as a Grignard reagent, where you had 2 carbons, here's your 2 carbons, you would need this as your ketone. Notice that this ketone here is different from this ketone. This is 2-pentanone, this is 3-hexanone. Different ketone, different organometallic. A third possibility is to make this bond right here. And in that case, you're going to need 3 carbons. So your Grignard must have 3 carbons here, which means your ketone will look like this, 2-butanone, which is essentially right here. So again, think carefully. Of course, as you know by now, my questions are designed to have you not only know the concept, but equally important is to apply these concepts. So if I asked you to make this as your target molecule, I would expect that we would get different answers here, different correct, reasonable answers, where one student would probably use this, another student would use this as a carbonyl, and use this as a carbonyl, but recognizing that the Grignard reagents that's used for each of these syntheses will have to be different. Okay, let's look at another application using the Grignard reagent. So, another possible question could be, starting with this as your starting material, your cheap starting material that you can get from the stockroom, and you need this as your target molecule, a carboxylic acid. What reagents and reaction conditions will be used here to get that process? So as we did earlier, carry out your observations and your retrosynthesis strategy. Let's do the observation. Number 1, this group is a carboxylic acid. So the moment you mention carboxylic acid, you should recall that you can make a carboxylic acid by the reduction of carbon dioxide, followed of course by hydrolysis. And that reduction involves a Grignard reagent or an organometallic reagent with carbon dioxide. Notice again, one observation is this bond here is a new bond. So we'll have to make that bond because it's not here. So, putting all of these pieces together, how can we do that? Let's see. So the first observation is this is carbon dioxide. We can reduce this is carboxylic acid. We can reduce carbon dioxide with a Grignard reagent to get this as our carboxylic acid. But we need a Grignard reagent. Here is our Grignard reagent where this is partial negative and partial positive over here. So this is the carbon that will react with this CO2. So here's that carbon negative, here's that carbon positive from CO2. And of course, after hydrolysis, we have here our proton. But this is not our starting material. Our starting material is a organohalide. We know that we can make a Grignard reagent from organohalide by mixing it with magnesium in the presence of a solvent. The solvent is typically diethyl ether. For shortened form, we just typically write ether. So once again, to make this molecule, which has a carboxylic acid, you will need a Grignard reagent reacting with carbon dioxide. To make this Grignard reagent, you need an alkyl halide here reacting with magnesium. Let us look at the reaction of a Grignard or organometallic with another functional group that looks pretty close to the carbonyl. It's called an oxirane or an epoxide. This is the structure. We've seen that before in the previous chapter. The key here is that this carbon is partially positive. This carbon is also partially positive because of this oxygen, which is electronegative and pulling these electrons here towards itself. So therefore these bonds here are polar covalent bonds. The nucleophile here in our organometallic reagent or reducing reagent in this case is negative, so it will be attracted to one of these carbons. We have observed over the years of carrying out reactions like this is that the nucleophile is always attracted to the carbon that's least crowded, less crowded carbon. So here we have a hydrogen and a hydrogen bonded to this carbon. This carbon here has a alkyl group and an alkyl group. So this carbon here is less crowded than this carbon. So therefore this reaction will take place here at this carbon, and these electrons will swing out, breaking this bond here to form a salt, an alkoxide salt. So here's our nucleophile with its electrons right here and our salt. As you can expect, this is a salt, so in organic chemistry we prefer the neutral molecule, so the alkoxide reacting with an acid, which because this is a base, will give here the alcohol. The key here though is that the nucleophile reacts with the epoxide to give us here a alcohol which has 2 additional carbons, at least 2 additional carbons. Let's see if we can apply that concept. So here we have organomagnesium, good old Grignard reagent, methyl Grignard, 1 carbon. And this is a specific epoxide, ethylene epoxide or oxirane. As you can imagine, this negative will react with this carbon. Why that carbon? It could be either carbon, because they have 2 hydrogens bonded to it. So none is more crowded or less crowded than the other. The product after hydrolysis is a alcohol with, of course, 2 extra carbons here bonded to the methyl Grignard. So again, I want you to think ahead. We can in fact make larger molecules, larger alcohols from a smaller compound such as a methyl Grignard reagent. Here's another variation. If you had as your starting material methyl chloride, can you make the same product here? Yes, you can, because this will not react with the oxirane or the epoxide, because this carbon here presently is not negative. In fact, it is partially positive because it is bonded to a very electronegative chlorine. So again, this carbon here is not negative, but you can make it negative by converting it into a Grignard reagent as shown here. That Grignard reagent can react with your oxirane followed by hydrolysis to form the same propanol. Notice 1, 2, 3 steps. You must include your steps when you're doing a multi-step synthesis. Let us look at another reducing agent, catalytic hydrogenation. In this case, hydrogen is a reducing agent. Of course, as you know, hydrogen is not very reactive, but in the presence of a catalyst, such as platinum or palladium, a reduction can take place where molecular hydrogen is delivered to, for example, an alkene in a stereospecific manner. So this just gives you an illustration of why the stereochemistry occurs, or the outcome of the stereochemistry. Here's the metal surface, which could be platinum or palladium. It holds the alkene in place and also the hydrogen in place. So what it does, it delivers the hydrogen on the same side of the alkene. So it's called a cis addition or a cis product. That's why it's stereospecific. So in this reaction here, using hydrogen and platinum as a catalyst, notice the stereochemistry, same side. So again, in writing the products for these reactions, make sure you include the stereochemistry, because that's very important. Here's some more examples. This molecule reacting with hydrogen will give this as a product. Notice the stereochemistry is not important here because one hydrogen is here and the other one is here. So there's no specific stereochemistry across this bond here. This one, however, as you've seen before, has a specific stereochemistry where these two hydrogens are on the same side. Notice it could be both dashed, or both wedges. Okay, but make sure they're not trans to each other, but they are on the same side. Let us look at another type reducing agent, and this is called the acetylide anion. Acetylide anion. Let's see what it looks like. If you have an acetylene or alkyne with an hydrogen here, you will recall from the chapter on hybridized orbitals, this is an sp orbital, which means that this is an sp carbon, which means that this hydrogen here is acidic. If there's a reaction with a base, a very strong base, such as sodium amide, it pulls off this hydrogen to form here this base, conjugate base. As you can see, here's a pair of electrons. It is negative, so therefore it can reduce or react with a partial positive reactant. Here's a specific example where we have an acidic hydrogen with sodium amide to give this as our nucleophile here, which can now react in a similar manner as the organometallics that we've seen before. They're not as reactive as lithium aluminum hydride or the Grignard reagent, but still yet it will undergo similar reactions. Let's look at some examples. It is not surprising that if you had formaldehyde, and here we have our nucleophile, acetylide anion, it will react here. These electrons will swing out, and in a second step we can put on this proton. But the bottom line is that we have now added this group to our formaldehyde. Here's the formaldehyde portion right here, and we've now added 1, 2, 3 carbons that now have the carbon-carbon triple bond. Here's another example, an aldehyde, not surprising. These electrons here can react with this positive carbon to form this product, which we'll call an alkynol, secondary of course, and we've added here these carbons to this aldehyde. So notice this molecule here is larger than our starting material. So as you can imagine, when you're doing synthesis, you have to think of a strategy where you can combine two molecules like these to make a larger molecule as shown over here. The third example, not surprising, taking a ketone and reacting it with the acetylide, which has an unshared pair of electron, nucleophilic. It will react right here, and these electrons, of course, as you can imagine, will swing out. After hydrolysis, it puts on that proton, and here is the tertiary alcohol, but it's much larger because we have introduced here more carbons and also a functional group called the alkyne. Let us apply this strategy. So if you're asked on the quiz or on the test to carry out this transformation, notice these molecules are getting a little larger now as we go along. Starting with the same molecule we had before, cyclohexanol. How do we make this molecule? As I mentioned earlier, before you put pen to paper, you will have to sit and do the observations and work out a retrosynthesis strategy. Let us do some observations here. Number one is that we now have this group here, 3 carbons bonded to the starting material to form the product, which means that whatever we had add here must have 3 carbons bonded, 3 carbons. In addition, we have introduced in the product here an alkyne, which is not in the reactor, which means that whatever we introduce here as a reactant, it must have an alkyne functional group. Now the pieces are coming together. We observe here an alcohol and a tertiary alcohol, and we know we make tertiary alcohols, or one way of making tertiary alcohols is from the reaction with a ketone with a good reducing agent that has carbons. So we need to put these pieces together. Again, this is organic chemistry. Is how well you can make observations, how well you can remember the concepts. Equally important, how well you can apply the concepts that were covered. This, of course, is called a retrosynthesis strategy. So we have to develop a strategy to solve problems. That's mainly organic chemistry. The application is right here. So again, starting with this as our starting material, what do we mix? And what steps, reactions do we take to get this as our final product? We've done the observations in the previous slide, and we've done the type reactions that are needed. We just need to put them together in a retrosynthetic strategy. So we need to bring this in from the reaction of a ketone with an acetylide. So here is the acetylide that's needed. Really, this is the more important part because it's a salt. And here it is. We have a ketone, we need a ketone, but our starting material is not a ketone, and we know that we can go from an alcohol to a ketone by a specific type reaction known as oxidation. And again, I chose here potassium permanganate as my reducing agent, but you could choose any strong reducing agent to go from reactant to this intermediate here. So once again, in any quiz or definitely tests from now on, as you've seen, we have synthesis. There's always at least a couple of synthesis problem. Now you can see why. Because it gives you, the student, the chance to carry out that scientific approach, do observations, come up with a strategy for solving a problem utilizing the concepts that are covered in organic chemistry. Let us look at another type reduction, and this one is dissolving metal. Let us see how it works. Looking at the periodic table, you can see lithium, sodium, and potassium are all to the extreme left of the periodic table. And of course, as you know, they are extremely reactive. Why are they reactive? Because the electronic configuration here is not very stable, because over the years we have defined an electronic configuration as stable as one that is similar, the same as the noble gases, the ones to the extreme right on the periodic table. So as you can see here, lithium gave up one electron. It gains the electronic configuration of helium. If sodium gave up one electron, it gains the electronic configuration of neon. And of course, if potassium gave up one electron, it gains a stable noble gas configuration. So the bottom line is that these elements here are extremely reactive, and they are reactive because it gives up electrons, and we know from definition that a species that gives up electrons is a reducing agent. So these are all extremely strong reducing agents because of the potential to deliver electrons. Let us apply that concept. So here's benzene. We'll see next semester that benzene is a very stable molecule, non-reactive. That's why it's used as a solvent. But you take benzene and put sodium metal in its presence. Notice the solvent here is liquid ammonium. You can't use water because it's acidic to an extent. So we have a special solvent here called liquid ammonia. It will deliver one electron to the system. As you can see here, here's the electron. This is called a radical anion, because if you count the electrons, we have 2, 4, 6, and 1, 7. So this system here has one extra electron compared to benzene. As you can imagine, not stable, so it will grab a proton from the solvent to give a radical. Radicals are intermediates, they are not stable, so in the presence of more sodium, it will give here an anion. So remember, radical is one electron. Putting another electron in, we have an anion. An anion here can do a similar job as we had before, abstracting a proton from the solvent, ammonia, to give here a reduced 1,4-cyclohexadiene. So that's one reaction that's important in organic chemistry, is the reduction of benzene to give this as the product. This has a name because it was discovered by Birch, so it's called the Birch reduction, where we use here a very reactive metal in the presence of liquid ammonia to reduce benzene, for example, to 1,4-cyclohexadiene. Let's apply that concept to the reduction of an alkyne. Triple bond. So we have lots of electrons here. 2, 4, 6. Really 2 pi electrons. So we got 4 electrons here as pi electrons. Sodium, being very reactive, wants to deliver 1 electron. So it delivers one electron here to one of the pi bonds here. So now we have here 2 electrons and a radical. Just like we've seen before, these are 2 electrons here, but now we have 2 and 1 makes 3 electrons. So it's added 1 electron from sodium to form a radical anion. The key here, however, is that it's trans. Because, of course, as you know, electrons are negative, so they want to get as far away as possible from each other. So this is a trans arrangement. This anion here will react with the solvent to put on this proton here, so we have a radical. In the presence of more sodium, the radical, 1 electron, will gain another electron from the sodium to form here an anion. It can attract a proton from the solvent to form this bond here. Bottom line is, we have reduced an alkyne to an alkene. Here's the alkene. Equally important is that it's a trans reduction. This is a trans reduction. So as a review, if you add hydrogen, it gives you a cis reduction. If you use here a metal in the presence of a solvent such as ammonia, it gives you a trans addition. Okay, let us see how we can do that using a hydrogen and a catalyst. So here again, the same concept, but in this case, instead of having here your catalysts such as palladium and platinum, here we have a deactivated catalyst. So it's not as reactive. The bottom line is it's not as active a catalyst as just platinum, deactivated. So the bottom line here is the same concept applies. It holds the hydrogen on the same plane, and it also holds this triple bond, or 1 pi bond of the triple bond, in the same plane, and it delivers the hydrogen on the same side. So the bottom line is, if we use hydrogen in the presence of a catalyst that's not very active, we call it a deactivated catalyst. That process was discovered by Lindlar, so that catalyst is known as Lindlar's catalyst. And if you just write Lindlar's catalyst, we as chemists will understand. It's really palladium in the presence of another deactivating compound such as quinone, which makes it not as reactive. So if you take here this alkyne, notice this is an alkyne, in the presence of H2 and Lindlar's catalyst, or deactivated catalyst, what you get here is a syn addition, or a cis alkene. Notice the difference. It's a cis alkene using hydrogen and poisoned catalyst, or deactivated catalyst, compared to the previous reaction where we used a metal such as sodium in the presence of liquid ammonia, where we get trans addition. So this gives a summary. If you have this alkyne here and the reaction takes place in hydrogen and Lindlar's catalyst, you would get a cis addition. Take the same alkyne and react it with sodium in the presence of liquid ammonia, you get a trans alkene. Okay, so again, you can see where we're going with this. You'll be asked to synthesize different products. One may be a trans alkene. One may be a cis alkene. So you will have to carry out specific observations and determine specific reactions that are needed to get your target molecules. Lastly, we look at some additional reducing reagents. If you had here a carbonyl compound and you reacted with zinc amalgam, zinc in Hg, you can reduce this to the methylene unit, or two H's. The mechanism is in the book, but the bottom line here is that if you have this, a carbonyl, and you need to get a CH2, you can use this mixture here. This reaction was discovered by Clemenson, so it's known as the Clemenson reduction. Another similar reaction is if you have the same carbonyl and you want to get the same CH2, instead of using zinc amalgam, you can use hydrazine in the presence of base and heat. It will give you the CH2, the reduced product. By the way, and by the way, that mechanism is in the book, so you may want to take a look at that. But the bottom line is that you can take your ketone and get a CH2. I think this is the end of this lecture and the end of this chapter, chapter 10. So please go ahead. I know we covered a lot here. It will take some time for you to go through the video and the PowerPoints, and also the book. Make sure when you do your studies, you have your book right there beside you, so that you can pause the video or stop the PowerPoints and get your notes and literally work out similar examples. Because as you've seen from the quizzes and the tests and the tutorials, these concepts are the same, and some of these examples are essentially the same, except that I just change around the molecules, because we're really testing concepts to make sure you can apply them to solving problems. So continue to study hard. We do have a quiz this Thursday which will cover this material. The tutorial questions are very, very good in assisting you to understand this material, so make sure you work them through carefully. Again, I'll post the answers on Wednesday at 6, so you'll have enough time to review and get ready for the quiz. So continue to study hard. We're almost there at the end of this semester. Let's keep up the hard work, and I'll post another video before Thanksgiving, so you'll be ready for to end this semester. Okay? Continue to study hard. Okay? Bye.